Hey guys, back again. Because of SBAC testing, a lot of people have been absent this week, and also, sickness going around and whatnot. So here's an opportunity to catch up on Section 9.5. Hopefully this helps you out, guys. It is a little bit of time out of my day, but I hope it keeps everybody on track, especially with me being gone on Wednesday and Thursday this week. So there's your topic. There's your title. If you want to pause it and read that to yourself for a minute. I'm going to kind of go through this kind of quickly here to get people caught up. These first ones I want you to calculate, and I would pause this and spend 3 or 4 minutes, maybe 6 minutes. It took about 5 minutes in class today to catch up on this. For these first couple, I want you to first of all review the word similar and see if these rectangles are similar, see if the triangles are similar, see if these regular hexagons are similar or not. Then compare their perimeters and their areas. And I do want you to try to calculate perimeters and areas on these. Later on, we're not going to be calculating them. We're going to be just answering in terms of ratios, and there's a shortcut we're going to come up with. But for these first couple, do it the long way. So hopefully you figure out, okay, I'm trying to find a scale factor. Scale factor is where I match up corresponding parts. So like the long side and the long side should match up, and the long side and the long side should match up. If you match these up, you should get a 4:3 scale. And again, this is a good time to pause, try to work these on your own, and see if you come up with my values, and sort of confirm it at the end here. The perimeter of this thing, compared to the perimeter of this one, interestingly ends up simplifying the same 4:3 ratio. This perimeter is even 52. This one ends up being 39. If you reduce this, if you divide both of these by 13, you get back to a 4:3 ratio, which may sound kind of familiar because we did this in Chapter 7. This is kind of a review, that the perimeter ratio is equal to the scale factor, that's what I'm using for SF, for similar figures. Then you calculate the areas. This is obviously 160. Multiply on this one and you get 90. And of course you look at 160 and 90. Think about what that reduces. That reduces to 16 to 9. And I'm hoping you eventually see sort of a connection between the scale factor and that. I'm not going to reveal it yet. We'll talk about it again in a minute. So try the same thing for the triangles. Match up your parts. Might want to pause again. Come up with a 1:2 scale factor or a 2:1 scale. You calculate the perimeters. I think they end up being 30 and 60, which coincidentally, interestingly, is also 1:2. You find their areas. This one's area ends up being 30. This one's area ends up being 120. And if you divide both of those by 30, you get to a 1:4 scale. Sorry, 1:4 ratio for areas. And again, there is a connection between these numbers and the scale factor, between the area ratio and the scale factor, and you might remember it at this point. For these last two, I don't want to actually calculate anything. I want to quickly go, if they're regular, all the sides are equal, all these sides are equal, so they're going to be an 8:12 ratio or a 2:3 ratio if you simplify that scale. You could find the actual perimeters, but I'm hoping by now you realize the perimeter ratio is the same as the scale. Perimeter ratio is the same as the scale, as long as the figures are definitely similar. And in every one of these situations, the figures are similar. Hopefully by now you've seen the connection. Where does this come from? If you know the scale, how do you find the area ratio? If you know this scale, how do you find that? What do you do with 4 to get 16? What do you do with 3 to get 9? Because I want to do the same thing down here. 2 is now going to become 4. 3 is going to become 9. If you square those similar ratios, which, sorry about that, which probably makes sense if you remember the last chapter, Chapter 7, about similarity. We now are talking a lot about area being square units. Well, it's the scale factor squared is essentially what it is, which you'll see a rule in a moment here. We'll talk about this working out for all three of these problems. And anytime they're similar, there's this ratio rule for similar figures. So, and the given here is important. If two figures are similar, the ratio between them, the scale factor between them is A to B. You probably can fill in these next blanks just based on those warm-up problems. The perimeter is also going to be A to B. You don't have to add up all the sides to figure that out. So this is sort of the shortcut. Area ratio is this scale squared. So it's whatever A is squared to whatever B is squared. Take a minute to maybe try these two examples. This first one is a given pair of parallelograms that are similar. You cannot calculate the area or the perimeter for either one of these because I haven't given you the top piece. But you can calculate some ratios, which is what I really want you to do. Find the ratio of small guy to big guy in terms of area and perimeter. And it all starts from the scale. So hopefully you'll look at that and go, oh yeah, the scale factors, it's not 2 to 3, it's not 4 to 6, it's 4 to 10, because this entire side is 10. Reduce that probably to 2 to 5, which will be the same thing as the perimeter ratio. If you could actually calculate the perimeters, you'd know it's a 2 to 5 ratio. And of course, at this point, I'm hoping, as you get through this, you can understand, okay, if I have the perimeter ratio or the scale factor, I can quickly get my area ratio. It's just the square of those two values. It's a 4 to 25 ratio, which is kind of review from Chapter 7. I will say that we've done this in Chapter 7. But now, because we're talking about areas, I want to make sure I review it and re-emphasize it. What this is really saying is, 4 to 25 is almost a 6 to 1 ratio. It's saying 6 of these blue parallelograms would fit inside of this big red parallelogram. And it kind of makes sense. You can see 1, 2, 3, 4, maybe a little strip over here would be the 5th one, and a strip along the top would be a 6th one. It's approximately a 6 to 1 space ratio. Try the same thing on the triangles over here that are similar. They both share angle Q. Angles U and T are congruent. And again, the scale on this would not be 8 to 3. The scale would be 8 to 11, because you're comparing QR to QS. Corresponding sides on there would be 8 to 11. The perimeter ratio, even though you can't calculate the actual perimeters, perimeter ratio is the same thing. It's 8 to 11. And of course, the area ratio would be squaring this ratio. So it'd be a 64 to 121 ratio. And again, if we think of space, this is saying this entire space is like 121, and the orange space is only 64. Which, if you think about it, this is about half of this entire space. And I want to be careful. It's not comparing the triangle to this little trapezoid here. It's not an orange to blue ratio on there, and I'm calling that color blue. It might be gray on your screen. The ratio of orange to blue is actually 64 to 57. This is something I usually pause for in class and let you think about that. Where did I come up with 57? 64 came straight from here. Think about what I did with these two to get 57. And if you haven't figured it out yet, I subtracted this entire space. I called the entire space 121. If I subtract the triangle from that, that should leave me with this little trapezoid. So the trapezoid is basically 57. This is 64. They're almost equal spaces, a 64 to 57 ratio. It's almost a 1-to-1 ratio. This is the type of question you'll see on the quiz this week. You've got to be able to do kind of all those parts. Get the scale factor for overlapping figures, identify perimeter and area ratios, and then go one more step, which is this is the only thing that's really new, you've never done before, because it's the area addition postulate enacted in there.